Good afternoon, or evening, or morning, depending on when you're looking at this. I'm going to go through and solve several force problems. I've got examples, which will be listed up here. This is example 0. It's the easiest problem. An anchor is held up by a heavy chain with 5 links. Oh, the anchor is 50 newtons. Each link weighs 5 newtons. Draw a free body diagram for points A and B. One of the things we're going to want to remember when we use force equations to do things, not so much with free body diagrams, but with equations, we're going to remember that our net force is equal to our total mass times acceleration. That's Newton's second law. We're going to think about coefficient of friction is equal to force of friction over force normal. This is a measure of how sticky or slippery an interaction between two objects is. For static friction, the coefficient will be greater than or equal to the force of friction over the force normal. Oftentimes, this reduces down to the maximum amount of static friction, which means this equation could turn into this equation. Finally, for an object near Earth, we have the gravitational weight, or force, sometimes called the weight, is equal to mg. The gravitational force, if we think of universal equations for that, we use gravitational constant, which is 6.67 times 10 to the negative 11th, multiplied by the mass of the first object, multiplied by the mass of the second object, all that divided by the distance between the centers of masses of the two objects squared. So those are things to keep in mind as we go along. You may want to write those down. They're on your formula sheet, or versions of this are on your formula sheet. All right, so let's take a look at point A right here. If I have point A, I know that it is not moving, it is not accelerating, so therefore the net force has got to be 0. So therefore the force downward would equal the force upward. Well, here this is a 50 Newton anchor, 5 newtons, 5 newtons, 5 newtons, 5 newtons, 5 newtons. So 25 newtons of weight in the chain. So point A, it doesn't know which part of that weight is the anchor of the chain. All it knows is there's going to be a tension force down at that point. Or pardon me, there's going to be a gravitational force down at that point and a tension force acting up. Actually, what I should do is I should redraw this because it's a little unclear as to whether the tension force is going up or down. So if this is now a light string and that's the ceiling, hey, it should be able to make sense to you that the tension force has to be acting up. The gravitational force on those objects down there would be acting down. So I would say something like this. F grav, or you could say mg, and tension. So at that particular point, those would be equal to each other. That doesn't look that great. And that would be 75 newtons. This would be 75 newtons as well. I'm going to assume that there's a little light string in there as well. So this is, by the way, at point A. At point B, the gravitational force acting down on the anchor is going to be 50 newtons. And the tension upward caused by this link of this chain will also be 50 newtons. I'm going to put 2 hash marks there since they're not the same size as this one. So what that says is if we have a heavy chain, so something where the mass or the weight of the chain or rope is not negligible, that top link has to be the strongest one because it's holding up the weight of everything else below it. Again, hopefully that helps. Welcome back. Right now I'm going to solve the example 1. We did example 0 before in terms of forces and the equations which might be shown right here. So if you remember these, Newton's second law, friction, weight, gravitational force near the Earth, and universal gravitation, which we'll really look at later in the semester. So In this case, we've got an example of a fish who's met its demise, and it's hanging from a string here. This string is light, as are these two. This string is acting horizontally. This string is acting at an angle 30 degrees above vertical, or above horizontal. The maximum tension in this fishing line, or this string, is 22 newtons. So the question then would be, what would be the value of T2 and the maximum mass of the fish in order to have 22 newtons here? So we're going to, again, assume that it's hanging from these light strings. So the key thing in this aspect is to think about forces in each dimension. I know that if the fish is just hanging there, it's in equilibrium, and therefore the sum of the forces in the x direction, Greek symbol sigma, meaning summation, would have to equal 0. I also know that the sum of forces in the y direction would also equal 0. I didn't write that very well. So I know that T1 maximum is equal to 22 newtons. I also know that since the forces left and right have got to be equal to each other, that the horizontal component of T2 would also be a maximum of 22 newtons. So I'm going to think about this. I'm going to say F left would equal F right, or right, because these two have got to be equal in magnitude, acting in opposite directions. Well, what's the force pulling left? And I would think about this really at point B, which I'll label right here. I think this one I'm going to call point A, and that's point C. So point B is what we're really interested in. So this is going to be T1. This is going to be the horizontal component of T2, so it's going to be T2 cosine of 30 degrees. I know that T1 is 22 newtons. So I can say 20, and the cosine of 30 degrees is 0.866. So therefore I can say that T2 would be equal to 25.4 newtons. So we've got that part of it solved already, and I only really have thought about the horizontal parts here. To think about the mass of the fish is acted on by gravity, which is acting downward. The only force upward here would be the vertical component of C. So if I think about this, I'm going to say force up. That sounds naughty, fup, but it is not. And that equals F down. So upward forces equals downward forces. In this case, the upward force is caused by the vertical component of T2. So that's going to be T2 sine of that angle, which is 30 degrees. Force down is equal to mg. So when I think about this then, I already know T2 over here, it's 25.4. Sine of 30 degrees is 0.5. G is 9.8 newtons per kilogram. When we think about forces, we would think about the gravitational field strength as newtons per kilogram. We think about acceleration, we think about it as meters per second squared. In fact, they're equivalent units to each other. So this is going to be 12.7 equals m times 9.8. So when I rearrange that, I get the maximum mass of the fish. It's 1.3 kilograms. That's a little less than 3 pounds. That's not a huge fish, not a tiny fish either. So that's how to solve problems when we think about forces acting in both horizontal and vertical directions. By the way, there's a key word you should mention to your physics teacher at Central if it's Mr. McChesney. The key word is candy. If you say the key word candy to him, he'll give you a piece of candy. Isn't that awesome? I may or may not give a piece of candy, but I'd still like you to hear me say that to me, just to let me know that you watched the video.